All right, so just wanted to start off with a couple updates. I'm about halfway through grading the quizzes that were due Monday, and so my goal is to have those done tonight, so you have that feedback to help you as you're working through your exam. By the way, the exam, if you didn't realize, it was released yesterday, and it is due tomorrow night at 11:59 p.m. And again, that exam is just over Unit 3. And so, that's our Venn diagram sets and our probability with independent, dependent, conditional probability, all of those pieces. Okay. So again, I'm working on getting those quizzes graded. I will have them done today so that you'll be able to see that feedback and have it help you as you're completing your exam. Any questions for me before I jump into what I'm going to talk about today? All right. Oh, and most importantly, next week's spring break. So I hope everybody has a great spring break. And obviously we will not have lecture next week. We will come together when we and meet again in 2 weeks from today. So can't fail to mention that. Very important. I think I'm sure all feeling the need for a break. Oh, but that does remind me, with the spring break, the conditional probability activity, normally we've been having our activities due at the same time as the exam for that unit. I did push the due date for the conditional probability activity to the Monday after spring break, which is April 1st. And so if you don't complete that before spring break, you'll want to complete it while you're on spring break so that you have it ready to turn in when we come back on that Monday. And as always, I always advise, hey, work on it before you forget about it, right? So like as you're completing your exam, it might be helpful to do that activity as well, okay? All right, so today's content is about our intro to counting, and this is the content, that is covered in homework 14. And this is paving the way for more probability stuff that we're going to talk about. And what we're looking at today has to do with counting techniques related to something we call combinations and permutations. Okay, so let me share my screen. All right. So multiplication principle says that if we have n choices that must be made, and m sub 1 choices to make choice 1, m sub 2 to make choice 2, and so on, with m sub n choices to make choice n, then the total number of choices we can make is the product of all those values. So what does that look like? Well, if I have a Mr. Potato Head and he has 3 hats, 5 mustaches, and 4 different types of glasses, how many ways are there to dress him? Well, if we have 3 hats, for every hat he could have, for each of those 3 hats, he could have those 5 mustaches. And then for each of those 5 mustaches, he could have the 4 different types of glasses. And so previously we've looked at drawing tree diagrams for all of these possible outcomes, and this would just be insane if we tried to draw that. So what we're looking at is saying, okay, we've got 3 hats times 5 mustaches times 4 types of glasses, giving us a total of 60 outfits. Now that's not to say all the outfits are going to work, right? There could be some weird hats and weird glass combinations, but the possible outfits are 60. And again, we're getting that by taking the number of choices at each stage and multiplying that together. Now, they can get more complicated than just dressing Mr. Potato Head. So number 2 says a combination lock requires 3 numbers from 0 to 39, but you cannot have the same number twice in a row. So if we look at the numbers from 0 to 39, there is 40 total numbers there. So we have 3 positions on our lock, right? And for this first position, I have 40, okay? In the next position, I can't use the number that I had in position A, right? So I have to take that out, which means that I have 39 choices for that next position. Now, moving to my last position, if the problem had said you can't have the same number twice in general, then I would have had to take out the number for the first position and the number for the second position. But it's just saying you can't have the same number twice in a row, which means I could take the number I had on the first position and repeat it in the third position. But again, I can't repeat the one in the middle. So it gives us 39 choices here again. So in order to multiply or to come up with this, we need to multiply all of those put together. And again, the reason why it's not 40, then 39, then 38 is because I didn't say you couldn't repeat numbers total. I just said you couldn't have them twice in a row. So I could do A, B, A, right? But I can't do A, B, or A, B, B, right? Those are not allowed. You can have that number come twice in a row if it comes at the end. That's all I'm saying is that so whatever value we have in the first position, we can't have that same number in the second position, but we can have that number again in the third position, which would turn our total number of choices back to 40, but we can't have the second position repeat, which then drops it back down to 39. So if we multiply these together, we're going to have 60,840 total choices. All right. So let's get into some additional counting techniques. So we have the concept of factorial notation. So for any natural number n factorial, and that's not just like n exclamation point as in you're like really excited to say it. It's an actual mathematical operation. And so what it's saying that n factorial is equal to the product of all the values less than n down to 1. And this is a little confusing because let's say we have 5 factorial. That means it's going to be 5 times 4 times 3 times 2 times 1, right? That's what 5 factorial means. It's the number times all of the previous values down to 1. Fun definition to remember, 0 factorial is equal to 1. So we're going to look at the concept of permutations. And the big thing you want to remember with permutations, order matters. Okay, so if NPR, where you have n items taken r at a time, where the number you're taking is less than the amount that you have to choose from, and it's the number of permutations, again, like I said, n elements taken r at a time, then P of nr is n factorial over n minus r factorial. If you are plugging this into your calculator, you're going to do, so when I say calculator, I should specify, if you're doing this in Desmos, you're going to do NPR, and then it would be n comma r. That's how you would calculate that out. And so you notice you've got n factorial over n minus r factorial. And so how does this, what does this look like, right? So in number 1, it says, suppose we have 8 people running for office. How many ways are there to rank your top 3 choices? The fact that they're asking us to rank them tells us that order matters. And so this would be like saying, okay, well, I have A, B, C, A, C, B, B, A, C, and so forth, right? Like we're considering the position that we put those people in. So if I have 8 people and I want to rank 3 of them, we're looking at taking the permutation of 8 people, chosen 3 at a time, because we want 3 for first, second, and third. And that calculation is going to be 8 factorial over 8 minus 3 factorial. Now, if we think about what does this look like? Well, for my first choice, I'm going to have 8 people to choose from. The second choice, I can't rank person number 1 again. So now I only have 7 choices. And then for that last one, I can't rank person 1 or person 2. So my number of choices drops down to 6. Well, from the formula standpoint, we've got 8 factorial over 8 minus 3 factorial, which is going to be 5 factorial. And if we expand out 8 factorial, that's going to be 8 times 6, or excuse me, 8 times 7 times 6 times 5 factorial, all divided by 5 factorial. And the reason I'm stopping at that 5 factorial is because I can cancel those out. And you can see how I end up with 8 times 7 times 6, which reduces to 336. Now we're going to say that all of these people are equally likely, right? We're not adding any other conditions to why we would choose them and rank them and all of that business. In number 2, it says in a ballot, the candidates for each office are listed together under the office for which they're running. In an election, 6 candidates for one office and 5 candidates for another office. How many different versions of the ballot are possible? So in this situation, we aren't necessarily looking at a permutation because of the fact that we have, let's say we've got president and vice president, right? So there's 6 candidates for that position and 5 candidates for each of those positions. So if we were looking at this from a permutation standpoint, we could say it's like the permutation of 6 choose 1 times the permutation of 5 choose 1, which is a little needlessly complicated, because really, if I have 6 items and I'm choosing one of them, there's 6 ways to do it. So really it's just 6 times, and against 5 candidates, 5 ways to choose that, 5, giving us 30 total possible ballot combinations. So another thing we want to think about with like a special case of permutations has to do if we're arranging items that are repeated. Okay. And so we are going to say that order matters, because if I were to rearrange these letters and put an I first or an M first, those are different outcomes, right? But if we think about letters in general, there's no way for us to consider like the S's as being independent of each other unless we were to give them colors, right? They would need something additional to define that they are different from each other. So in general, we're going to look at this and be like, oh, well, there's 4 S's there, an S is an S and an S. So if you are trying to arrange something and there's repeats of it, you need to remove those double counts, those repeated values. So we want to look at what is repeated, right? So we need to know what are the number of I's, the number of S's, and the number of, P's. Because in Mississippi, we are repeating I, we are repeating S, and we are repeating P, right? So, how many I's do we have? What do we think?
4.
4. Okay, what about S's?
4.
Okay. And P's?
2.
2. So then we need to think about how many total letters do we have?
11.
11. So we know that if we have 11 letters, there's 11 factorial ways to arrange them, right? But there's letters that are being repeated, right? And S's and S's and S. So we need to remove the double counting that would happen with S's repeating and us not being able to not be able to tell the difference between them. And so then we're going to put in their denominator 4 factorial times 4 factorial times 2 factorial. Okay. And what this is doing is the denominator is removing the duplicate letters. So when you're calculating this in Desmos, you can put this in as 11 exclamation point divided by, like you can put the whole thing in. If you are not putting, excuse me, if you're not putting this into Desmos, you need to, when you think about order of operation, we need to satisfy our numerator, we need to satisfy our denominator. When I say satisfy, we need to calculate it out. Excuse me. So you'd actually need to find what is 11 factorial, right? In the denominator, you're taking 4 factorial times 4 factorial times 2 factorial. And so again, you're simplifying that numerator and simplifying that denominator before you actually divide them for the final answer. So I want you to go ahead and do that calculation and send me your answer in a direct message. All right, so if we plug this all in, we come up with a final answer of 34,650 number of ways that we can rearrange the letters of Mississippi and have, you know, them all be unique. So the idea of uniqueness and order mattering, so when we move from permutations where order matters, right? A, B is different than B, A. And then into the concept of combinations where order doesn't matter. And one of the things that I think about all the time with order not mattering is think about the toppings you put on a pizza. I am a type of person who says it's like crust, sauce, cheese, all the bits, right? There's areas in the country where they do crust, sauce, all the bits, then the cheese on the top, right? But if we say that we have to agree that it's crust, sauce, cheese, the order that you put the toppings on after that point, right, doesn't matter to the flavor that you experience in your mouth, right? Like it's like a combination pizza is what I'm thinking about, right? So you've got sausage, pepperoni, green peppers, onions, mushrooms, olives, all of those things, when you put them together and you take a bite, it tastes like a combination pizza, right? So the order doesn't matter with combinations. And so what does that look like? So in general, a combination is a subset of R elements in an N element set without regard to order. The difference between permutations and combinations is that permutation order matters. Combinations, it does not. And so we denote the number of ways of choosing that is C of NR or N over R. Now, when we look at the actual calculation, the combination of N items taken R at a time is N factorial divided by R factorial times N, oops, making that look like an H, times N minus R factorial. So the difference you can see here in this calculation, the difference between this calculation and our permutation calculation is that extra piece of R factorial. And that R factorial, much like in the Mississippi example, that R factorial is removing the duplicates. And so it's removing like the pizzas where I said, okay, well, it's pepperoni, sausage, onion being separate from pepperoni, onion, sausage, or sausage, onion, pepperoni, or like this is the same pizza, right? So that R factorial, that extra piece is removing those double counts. Because again, with combinations, order doesn't matter. Okay, and so one thing I want to note is that when you're writing your notation, don't put a line because now you're talking about a fraction, right? You'll notice that it's just N over R. So you're talking about, again, N items taken R at a time. So we have a 5-member committee and we want to select the 5 members from a Senate containing 100 members. How many ways to do this? Committees are a really common thing because it's a group, right? The order that we select them doesn't matter unless we're giving them specific jobs, right? So a group of 5 people is still the same experience no matter the order that they're chosen in, right? And so we want to do the combination of 100 people taken 5 at a time. Now, if you did this using the formula, that's going to look like 100 factorial over 5 factorial times 100 minus 5 factorial. Which to simplify it is 100 factorial over 5 factorial times 95 factorial, which continuing to simplify would be 100 times 99 times 98 times 97 times 96 all over 5 factorial. What I did there is I took the 95 factorial out of the numerator and the denominator. You'll see these can get kind of tedious. My expectation is that you are using your technology to solve these. So in Desmos, instead of NPR, we're going to do NCR of 100 taken 5 at a time. And this comes out with a crazy big number. So it's going to be 75,287,520. So there's 75,287,520 possible ways to select a 5-person committee from a group of 100 people. Now, as I said, order doesn't matter with combinations. Sometimes order does matter. As I said, if we're selecting people and they have specific roles, the order matters. So in number 2, it says a space shuttle crew consists of a shuttle commander, a pilot, and 3 engineers. The shuttle commander and pilot are to be chosen from 8 candidates, and the 3 engineers are to be chosen from the 12 candidates. We're going to assume that the 3 engineers are all of equal rank. An engineer is an engineer is an engineer. And so when we think about this problem, was there a question? I'm sorry. Oh, I thought I heard something. When we think about this problem, we've got 2 things happening. We've got a pilot and a shuttle commander, and then we have 3 engineers. So for this stage, order matters. And for this stage, order doesn't matter. So what we're going to break this up as is that we've got a permutation of 8 candidates chosen 2 at a time because the order matters. And then for the engineers, we have a combination of 12 candidates taken 3 at a time. Now, just like with our multiplication principle and thinking about Mr. Potato Head's outfits, for every hat, i.e. every combination of pilot shuttle commander, there are 3 different engineers that we can choose. So in order to come up with our total number, we need to multiply between those in order to have our final answer. So I want you to calculate that and send me your answer in a direct message. So I would suggest always using Desmos. So for the permutation part, you're going to do NPR of 8, choose 2. The combination part, you're going to do NCR, oops, of 12, choose 3. Okay. So if we look at our, in Desmos, we've got, if we do NPR of 8, choose 2, that's going to give us 56. And then NCR of 12, choose 3 is going to be 220. If you were to do this by hand, right, we think about the permutation of 8 items taken 2 at a time would be 8 factorial over 8 minus 2 factorial, okay, which would be 8 factorial over 6 factorial, which reduces to 8 times 7, because if we expand out 8 factorial, it's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, from the 6 times 5 times 4 times 3 times 2 times 1, from that point down, that whole bit is 6 factorial. So we can cancel 6 factorial from the denominator with 6 factorial from the numerator, and then just be left with 8 times 7, which is how we come up with the 56. For the NCR portion, we have the combination of 12 items taken 3 at a time. That's going to be 12 factorial divided by 3 factorial times 12 minus 3 factorial, which reduces to 12 factorial over 3 factorial times 9 factorial. Again, in the numerator, we're gonna have 12 factorial. In the denominator, that 9 factorial cancels out to where we only have 12 times 11 times 10 left. And in the denominator, that 3 factorial is 3 times 2, which is again how we get to 20. So multiplying 56 by 220, we end up with a total of 12,320 ways that we can create this space shuttle crew. So the piece here that is challenging is recognizing that there's part where order has to matter and part where order doesn't matter, right? And knowing how we treat those two separate parts. So again, with order matters, you always want to go with permutations. If order doesn't matter, we're going with combinations. And then that multiplication principle is telling us that between the two, we would multiply in order to come up with the total number. So questions about that piece?
When we take like quizzes, do you want us to write out the handwritten part of this or just like show a link to our Desmos work?
You can show a link to your Desmos work. If you did NPR into your in your calculator, if you did in Desmos NPR of that value, you could write just NPR of 8,2 and say what it's equal to. Obviously having a link to your Desmos is really helpful for me because I can see it, because if you come up with the wrong value, I can see if you accidentally wrote like 8,3 in Desmos and that's how you came up with that calculation, versus that you're like, well, I had meant to put this in, you know, so actually seeing your Desmos window is really helpful that way. So your choice.
Okay, thanks.
Yeah. Other questions? Luke, do you have a question?
No, I was just gonna say that your last explanation helped me.
Oh, good. I'm glad.
Yeah.
The last 3 examples I have are all about cards and selecting cards. I try not to do too many examples, especially because where we're going to after this piece. So like we're doing permutations and combinations. And then the next piece we're going to look at is probability with this stuff. And so classic, like there's always a ton of questions about like, what's the probability of this poker hand? And what's the probability of this poker hand? Blah, blah, blah. And well, it does show a lot of the like different like pieces that can go into doing these calculations. I do think at some point you can get a little too specific and you can lose, as they say, the forest through the trees in terms of like, we want you to understand the overall concept of what we're doing here. But I am going to do a couple examples because we can talk about what the number of combinations are. So number 3 says, how many ways are there to be dealt a 5-card hand? And so standard deck of cards, remember, has 52 cards. And the reason why it's nice to look at cards with combinations is that when you put them in your hand, if you're not looking at something fancy about them, right? You're just like, how many ways can I hold these? Like the whole hand that you're holding doesn't change if you put them in numerical order or if you put them in order of your suits, right? You group your hearts together, your diamonds together, blah, blah, blah. The whole thing, all 5 cards in your hand are still 5 cards. Like that doesn't change the value of it. You're just looking at how many ways can you choose 5 cards. So because this doesn't change the order, right? Order doesn't matter in creating this group of cards. This tells us that we need to use a combination. And so we want to choose 5 of them. So we're going to do the combination of 52 cards taken 5 at a time. Okay. So 52 cards taken 5 at a time is crazy big, like shockingly so. And this is why the probability of poker hands is so low. So 52 cards taken 5 at a time comes out with 2,598,960 possible outcomes, which is nuts. Like that's so many, right? Where things get interesting too is when we start talking about specific types of hands. So there is a 5-card set that you can get dealt. It's called Royal Flush. And a Royal Flush is when you have the Jack, Queen, King, and Ace, all of the same suit. Okay. And so if we think about how we want to calculate this, we want to think about what is specific about cards. And so we know that there are 4 suits, and we want to get all 5 of these numbers, right? We want 5 specific cards. So when we're looking at the different pieces that make up a royal flush, partly it's the suits, partly it's the cards specifically, right? And so to calculate this, we're looking at the combination of 4 suits, choosing 1, times the combination of the 5 cards we want and choosing all 5 of them. Because we're specifying that we want those specific cards, and really those specific cards, there's only one way to choose them. Where things get varied is which suit, right? Are they all going to be hearts? Are they all going to be diamonds? Are they all going to be clubs, spades? So the combination of 4 items taken one at a time, meaning 4 suits choosing 1, we've got 4 outcomes there, and 5 cards choosing all 5 at once is 1 outcome, giving us just 4 ways to be dealt a royal flush. Now, this homework does not deal with this, but if we think about the probability of a royal flush, this is why if you are playing 5-card hand poker in Vegas, granted they're dealing from a couple of decks at a time, but a 5-card hand in Vegas, the reason why like the payout would be so big is because the probability of actually getting that royal flush is those 4 possible outcomes out of that 2,598,960 ways to get it, which is super tiny. The probability of that happening is oh my gosh, let me count all the zeros. 1. Like that's so tiny. And again, the probability aspect, let me like kind of put a bubble around that, because that's what we're going to do later in like homework 15. Today we're talking about just how do you count that stuff, right? How do you do the combination piece? The next piece is obviously we're going to extend it with the concept of probability. But I wanted to give you an idea of like, why are we counting this? Where are we going with it? Well, we're going to be looking at finding the probabilities of those hands. And so turns out getting a royal flush is real rare, real hard to do. So number 5 says there are many ways, or how many ways are there to be dealt a flush? And just a flush, it's 5 cards of the same suit. We're not saying it has to be a royal flush. It just has to be 5 cards of the same suit. So what do you think in calculating number 5 is going to be the same as what we did in number 4?
Can you say that again?
So thinking like the calculations I did in number 4, right? Is there anything from that I would use in my attempt to solve number 5?
Maybe the 4 and 1.
Okay. So the
Yeah.
4-1 has to do with choosing the suit, right?
Yeah.
So the flush tells us we want 1 suit, which in the problem above, we found by doing the combination of 4 suits choosing 1, right? So that piece we've got the same, right? So the second piece is that we just want to choose 5 cards. I'm not limiting them to 5 specific cards. I'm choosing 5 cards for some number. So how many cards are there to choose from within one suit?
13.
Mm-hmm. So what we're looking at is suit times 5 cards, right? And of those 5 cards, we can choose from 13 of them. So we're gonna have the combination of 4 suits times the combination of 13 cards, taking 5 of them, because there are 13 cards in each suit. So I want you to calculate that and send me your answer in a direct message. So we know when we're doing the combination of 4 items, taken one at a time, we've got 4 outcomes there, right? The piece we don't know is the combination of 13 items, taken 5 at a time. So we're dealing with a combination because of the fact that we're just choosing 5 cards. The order we're choosing them in does not matter. So if we do the combination of 13 items, taken 5 at a time, we come up with 1,287 ways to choose those 5 cards from a set of 13. We then have to multiply it by 4 in order to account for the number of ways we can do this for each of the 4 suits. So multiplying those together, we come up with a grand total of 5,148. And that's the total number of ways we can get a flush. All right. That is everything I had for us to go over. As I said before, we've got exam 3, right? Exam 3? Exam 2. What exam are we on?
Exam 3.
3. Exam 3. So exam 3 is due Friday, 11:59 p.m. It is obviously available right now. I am going to finish grading your quiz 8s today. I hope to get them done before it's too late tonight, so you can at least look at the feedback. And then don't forget also the conditional probability activity. I did move that due date to April 1st for when we come back from spring break. But don't delay, right? We don't want to come back and be like, oh God, we forgot about it, right? So maybe again, my nudge is for you to still do it as part of your exam preparation. But if you don't have time right now, I completely understand. But you do have that due when we come back from spring break. So we won't meet next week because of spring break, but we will meet in 2 weeks. Okay. Any questions for me before I let you go? No? Okay. Well, I hope everybody has a great spring break. I'm not doing anything, but I hope you guys all get to do something fun and will come back and tell me about it. I'm probably gonna clean my house. Real exciting stuff happening.
I'm going to catch up on all the stuff that I'm behind on.
Ooh, I'm doing that too. I was laughing with some colleagues. So I was like, I don't even know this break concept because I have so much missing, like not like missing, but like I have so much back stuff that I need to do to